In this video, we're going to talk about 7.5, which is work. We also may discuss a little bit about center of mass of a planar lamina. I'm not sure if I've got an example of that in here or not. That is part of these applications of integration that you will need to know. So if I don't have an example of that, make sure that you pay attention to your notes from class where your teacher goes over that, because you will more than likely be tested on that. But the objectives here for sure are to find work done by a constant force and to find work done by a variable force. This is a very simple situation. If it's a constant force, this is a harder situation. This is pre-calculus, and this is calculus. So this requires integration. This is just a basic formula. Okay. The concept of work is important for scientists and engineers. It's used to determine the energy needed to perform various jobs, which can then be used to determine the amount of fuel needed, just as an example. So work is done by a force when it moves an object a particular distance. Force can be applied by a constant or variable force, but work is done by applying a force over a distance. So work done by a constant force, and if an object is moved a distance d in the direction of an applied constant force F, and it's important that we talk about in the direction of, because forces are vectors, then the work done, which is also a vector, by the force is work is in the direction of the force there times the distance, like that. And those are really vector quantities. Like I'm saying, the distance is not going to affect things since it's a scalar quantity here if it's a constant, but we have four fundamental forces that are going to give us some applications. So we have gravitational force. We have electromagnetic. It's everything to do with electricity and magnetism. We have the strong nuclear force. And we have the weak nuclear force. And don't let the word weak fool you, that is weak compared to the strong nuclear force, but it is still very strong. Lots of energy there. When that energy is unleashed, that's where nuclear energy comes from. Think of a thermonuclear reaction when that goes out of control. And so useful to think of force as a push or a pull that changes the state of rest or state of motion of an object. So first, let's think of lifting an object. And really, it has to do with this, the work has to do with the change in potential energy here. So change in potential energy. I'll just fill you in that potential energy in physics is mgh, where h is how high off the ground you are, and your work that's related to gravity here is your change in potential energy. So determine the work done in lifting a 50-pound object. That would be its weight mg, 4 feet in the air. So you went from 0 feet to 4 feet. So it gained potential energy. So W is going to be equal to its weight, 50 pounds, times 4 feet. You've done 200 foot-pounds of work. And so the unit of work in the imperial system, or the US customer measurement system, or the engineering system, however you refer to that, is foot-pounds. So we have, just to show you a picture here, you had an object that was down here, that its initial position was at 0 feet off the ground, and you call this y sub 0, and you moved it. Delta y is 4 feet, so its yf is 4 feet, and this was a 50-pound mass, so your delta y was a positive 4 feet, and so you have your mg, your weight is mg, your h is right there, and you had 0 potential energy down here when you were at 0 height. Now you have a potential energy up here of mgh, 200. And so 200 minus 0 is 200. There's your work, and that's in foot-pounds based off of my units. So again, measurements here, foot-pounds, or FT-LBS is work. When I see a hyphen in a unit like that, that implies multiplication. Pounds are a unit of force. Feet are a unit of distance, so this makes sense that work is equal to force times distance. In the metric system, international units, we're typically going to use joules, newtons, and meters. So the joule is a newton meter. So our joule is our unit of work. Newtons are a unit of force. Meter is a unit of distance. 1 joule is equal to 1 newton meter. So in the centimeter gram second system, this is a little bit different than what we normally use with the metric system. But we have work as measured in ergs, ERG, and the unit of force is going to be the dyne, dyne, that will abbreviate dyn, and the distance will be in centimeters. So you see that these are much smaller distances and probably smaller units of force and work. So conversion factors that are important to know here is that a foot-pound is approximately 1.35582 joules. And you can write that as 1.35582 times 10 to the 7th ergs. So 10 to the 7th ergs is 1 joule, is what that's telling us. So that's approximately 0.73756 foot-pounds. 1 newton is approximately 10 to the 5th dynes, and that's approximately 0.22481 pounds. And 1 pound is approximately 4.44822 newtons. We may need to do some conversions in some of our problems, but that's going to be unlikely because typically our problems all stay within the same system. So that's more of a physics engineering thing to need to know those conversions, but those are important conversion factors that you may want to make note of. So we require calculus to determine work done by a variable force that is applied to an object. The amount of force is changing over time as the object changes position. So consider an object that's moved along a straight line, x equals a to x equals b positions by a continuously varying force, f of x. Let delta x be a partition that divides the interval a to b in n subintervals determined by, you already get the idea, we're going to do a Riemann sum here if you're seeing n subintervals like this. So delta x sub, and I think they're using a letter there that might be an n. I'm not really sure, but I think it's an I. Okay, it's an I. So delta x sub I is equal to x sub I minus x sub I minus 1 for each I equals 0, 1, 2, so on to n. We're using I as our index. Don't think of I as the imaginary number. Choose C sub I such that C sub I is somewhere between x sub I minus 1 and x sub I, then f of Ci is the force at partition Ci, and we can approximate the work done on the interval xi to x sub I minus 1 as delta Wi is equal to f of Ci delta x. Should be the other way around. Minus 1 that. You have to have your lower boundary on the left. So the sum of the work, now when I take the limit as n goes to infinity, that's the same thing as delta x going to 0. This delta x is going to become a dx. The ci is going to be replaced with x, and my limits are going to go from a to b. Delta x is equal to b minus a over n here. So we're going to, if we would be going this way, that's how we'd find out what delta x was. You can also formulate work as a summation of increments of vertical distance. So we can just change our variables here from x's to y's, and it works just as well here. So I just showed you an example here where work was being done in the vertical plane here with potential energy. We'll do some examples where it's being done in the horizontal plane as well. So this is as delta x is going to 0. This is the same thing here as n going to infinity. Right there is going to become that. So in this definition, if an object is moved along a straight line by a continuously varying force, then the work W done by the force as the object is moved from x equals a to x equals b is given by this limit as n goes to infinity, or as the norm of the delta goes to 0, same thing, is the sum of I equals 1 to n of delta Wi is equal to the definite integral from a to b of f of x dx. A few important physical laws that we'll use in this section will be Hooke's law, which is about springs. So the force required to compress or stretch a spring within its elastic limits away from the its point of equilibrium is proportional to the distance. Well, yeah. So the force required to compress or stretch a spring within its elastic limits is proportional to the distance d that the string is compressed or stretched from its original length. So that distance that it's going to be stretched is going to be d. You'll see that distance as an s sometimes because of what we just did previously with length being an s. So you may also see f equals ks. That s is a distance as well. The constant of proportionality k, the spring constant, depends on the specific nature of the spring. but you'll be able to figure that out for that specific spring and then use it for the rest of the problem. So this statement is equivalent to saying that the force is proportional to the distance, or if we're using this, we're going to say force is proportional to the length that it was stretched. That length is going to be positive. If you're moving it with gravity to stretch it, or you're going to have to define a distance as positive. So, and another as negative. So this is going to be, you're going to have to define whether this was equilibrium as at 0. And if you move one direction from equilibrium, that's going to be positive. And you move the other distance away, it's going to be negative. So if you're stretching the spring, that's a positive direction. If you're compressing the string, that's a negative direction. All right, Newton's law of universal gravitation, the force F of an attraction between two particle masses, M1 and M2, is proportional to the product of the masses and inversely proportional here to the square of the distance. This is directly proportional here, and inversely proportional to the square of the distance d between the two particles. So directly proportional, that's going to be in the numerator. Inversely proportional to the square, so that's going to be in the denominator. We have this constant here. We normally would just call it k, and we would solve for it, but we know what that gravitational constant is. It is a known constant that we call capital G for the gravitational constant. If we're anywhere within our universe, the gravitational constant G is 6.67 times 10 to the, ooh, it's missing the exponent. Let me look that up. That's times 10 to the negative 11th. That got cut off somehow. So there it is. Meters cubed over kilogram second squared. So capital G is the gravitational constant. That's going to be a number that you're going to want to memorize. So similar concept, actually very related concepts. So we get that things that are big things, big objects, we normally think of this as like stellar bodies, things that are in space. So we use this idea here for big masses, and well, we use this for masses and distances. Doesn't matter whether it's big or small masses, but we usually are thinking of this stuff in like planets and asteroids and things pulling on one another, and actually being able to use this law to figure out that other things have to be out there in space because there needs to be more mass pulling on the object in this particular direction and stuff like that. Some pretty interesting stuff. So we found some planets and some comets and some asteroids and some moons and things like that just by knowing where to look because of Newton's law of gravitation. So Coulomb's law goes down to the subatomic, and it has to do with charges. And instead of gravitational force, this is that electromagnetic force that is part of this, but this is those forces that work between subatomic particles within the atom that are charged. So if we're looking at the force F between two charges Q1 and Q2 in a vacuum is directly proportional to the product of the charges and inversely proportional to the square of the distance between the two charges basically the same formula, only we don't have a known constant here like we have G. We just have K. When Q1 and Q2 are given in electrostatic units and D is in centimeters, F will be in dynes for a value K equals 1. So all that will make more sense to you when you get to physics and engineering, where you're going to be doing that. But let's talk about Hooke's law. Hooke's law is usually what we talk about in this class. We don't talk a ton about Newton's law of universal gravitation or Coulomb's law in this class. We usually stick to Hooke's law problems for our application. So a force F, remember that your force is 30 newtons, compresses a spring, so it's compressed, so delta x is going to be a negative 0.3 meters because we compressed it from its natural length of 1.5 meters. Find the work done in compressing the spring an additional 0.3 of a meter. So we need to find K. So let's not worry about which direction we're going in. Let's just worry about that the distance that we moved it, D, is 0.3 of a meter. And K is equal to what? So F is equal to KD. This is our initial information that we're given. So 30 newtons is equal to K times D. 30 newtons divided by 0.3 of a meter is equal to K. So 300. So 100 newtons per meter is equal to K. For every meter that I want to stretch the spring, I have to apply a force of 100 newtons. So now we're going to use Hooke's law, go A to B of F of W dx here. So this is going to be x times f dx, or f times x dx. So K, sorry, A to B of f dx, where f of x we just found was K x. So we're going to have dx and K we just found was 100, and A and B we're going from 0.3 away from equilibrium to 0.6 away from equilibrium. So this is going to be 100x squared over 2, 0.3 to 0.6. So this is 50 times 0.6 squared minus 0.3 squared is 50 times 6/10 is 600ths. 10ths squared, 900ths. 50 times 0.27 is 13.5 And my units here are going to be joules because they're Newton meters. So this was force times distance in newtons times meters. Remember, a joule is a Newton meter. All right. Let's do one of those examples of universal gravitation. A space module weighs 15 metric tons on the surface of the Earth. How much work is done in propelling the module to a height of 800 miles above the Earth? Use 4,000 miles as the estimate for the radius of the Earth. Do not consider air resistance or the weight of the propellant. So included will be weight of the body varies inversely as the square of its distance from the center of the Earth. So F is C over x squared, where x is the distance from the center of the Earth. So that gives us our work done is going to be a definite integral from a to b of f of x dx, just like it was with Hooke's law. That's what I was trying to write up there. So our force here is 15 metric tons. So 15 metric tons is equal to C over 4,000 miles squared. That's at the time that it's on the Earth's surface. We're going to have the radius of the Earth was 4,000 miles. So if we solve that, C is equal to 240 million, like that. And so W is going to be equal to 240 million. I'm going to actually write that in scientific notation, 2.4 times 10 to the 1258. 2.4 times 10 to the 8th over x squared dx. Going from 0, so going from A to B, we'll have to figure out what those distances are in just a second. So A is equal to the surface of the Earth is 4,000 miles from the center of the Earth to, now we want to go how high above, 800 miles above. So we want to go, B is going to be 4,800, like that. And so we get that this is 2.4 times 10 to the 8th, integral 4,000 to 4,800 of x to the negative second dx, 2.4 times 10 to the 8th, x to the negative first over negative 1, from 4,000 to 4,800. So that's going to give me negative 2.4 times 10 to the 8th times 1 over 4,800 minus 1 over 4,000 is going to be 10,000 miles metric tons, and just so happens that that nicely converts here, metric tons and miles are going to multiply to also give me joules. So that's 10,000 joules of work. All right, another problem. We're definitely going to be doing this type of a problem in this class. So a 20-foot chain weighing 5 pounds per foot is laying coiled on the ground. How much work is required to raise one end of the chain to a height of 20 feet so that it's fully extended? So start off with the chain is all coiled together here on the ground and has, like we said, zero potential energy down here. As we lift the chain, though, as we lift each foot of the chain, we're actually having to lift more and more of the chain. It's easy to pull the chain up at first. Then we have more weight to be lifting as we pull more of the chain up. That's why it's a variable force problem. So we have 5 pounds per foot. That's kind of our K. X is going to be our amount that we've lifted. Let's see, I don't have this problem done. All right, so I worked this one out as a supplemental example before. So we're just going to have this as a function of y. F of y is equal to the weight of the chain. And that's going to be F of y is going to be the distance y times 5, because distance or weight is in pounds, and then this is per feet. So we need to take 5 pounds per foot times the number of feet to get the weight of the chain that's in the air that we're lifting that portion. And we are going to have our work is going to be here where this is all here. There's 20 feet of chain. So we've lifted 0 feet of chain to we've lifted 20 feet of chain. And the weight that we are lifting is 5y. And we're integrating with respect to y. So this is 5y squared over 2 from 0 to 20. This is 5 halves times 20 squared is 400 minus 0 squared is 0. This is 5 halves of 400 is 5 times 200 is 1,000. And we are in work is being done in foot pounds here. All right. So back to the emptying of the oil tank or pumping a liquid example. So a spherical tank of radius 8 feet is half full of oil that weighs 50 pounds per cubic foot. This is a known thing, the specific, I think that's called specific gravity of oil. You're going to get a different number for water that you're going to want to memorize. We're probably only ever going to give you oil or water in these problems. And if we don't tell you the weight per cubic foot, then you need to know it for oil and water. If we give you something different than oil or water, we'll tell you what its weight per cubic foot is. So find the work required to pump all the oil out through a hole that's in the top of the tank. So let's draw a picture here that we've got a tank here that's in 3D. And I know we don't do a whole lot of 3D in this class, but Gonna do my best to draw a sphere here, a spherical tank, and we've got a hole that's in the top here that we're pumping the oil out of. And the oil was half full in the tank, like that. So I'm going to make this, let's see, I'm going to put this coordinate system right down here. I've put it on the bottom of the tank at the origin. So that means that this is the center point right here is going to be 0. And then it's going to be radius was 8. This point up here where the hole is going to be 0, 16, like that. So that makes this distance here of how much the distance that the oil has to travel. If the height of the oil at any point is y, then this distance is 16 minus y that it has to travel. So we'll take slices here, infinitesimal slices of delta y, and the weight of each of those slices there is going to be the delta y times the 50 pounds per cubic foot. We find the volume of this little slice here. Let's go ahead and show some of that. So the volume of each little slice, let's see, volume of representative disk, V equals pi r squared, and my H is going to be my delta y. So my R here is going to be x squared is going to be like this, where x squared plus y minus 8 squared equals 64, since I'm on a sphere. So x squared plus y squared minus 16y plus 64 equals 64. And so x squared is going to be equal to, let's just write it this way, x squared is going to be equal to 64 minus y minus 8 squared, like that. It's a difference of squares. So our v is going to be pi. This is of our slice. 64 minus y minus 8 squared delta y. Now that volume, when I multiply it times the 50 pounds per cubic foot, that's going to give me the weight of each slice. So the delta F is going to be 50 times pi times 64 minus y minus 8 squared delta y. Remember, the distance here that we're interested in moving it. So this is our f. Our distance that we need to move it is 16 minus y. And that gives us everything we need to set up our integral. W equals 0 to 8 of 16 minus y times 50 times pi times 64 minus y minus 8 squared dy. I'm not going to solve that just yet. Let me look and see if I did solve that over here. I did not. So that's good to just set that up. You can go ahead and keep working that out if you want to find out what the work is, but I'm just going to keep going here now that that's set up. I believe that you can take care of splitting up the integrals and getting to the answer there. So suggest a procedure for solving work-related problems. Determine a function that relates the information given about the force with respect to distance. Solve for the constant of proportionality. That's going to be different for all problems unless you are dealing with universal gravitation, where that's a known constant. Use the constant found in number 2 to finalize the function f of x for the integral and determine the correct limits of integration. Integrate, solve, and interpret the results. And don't forget your units. Remember, delta W change in work is equal to F times delta X, where X is distance. Really, we're dealing with displacements there since it's forces, but that's it for this video. And we will come back next time and start talking about chapter 8. I did not talk about center of mass in this video. So go ahead and make sure you know that application. We might have talked about that a little bit in, no, we didn't talk about that in Calc 1. So go ahead and look at some more examples of center of mass of a planar lamina. Planar lamina are things that are infinitesimally thin. They're basically going to be in such a way where you aren't considering the depth at all because they're sliced so thin. So they're like a plane. So that's another application of integration that you need to know how to do. All right, again, see you back next time for the beginning of our discussion for Chapter 8 topics.